Welcome to Let's Weld Something. I'm your host, Bob Moffett. A while back we did a video on MIG 101 where we put gun components together, O-rings, diffusers, contact tips, nozzles, and everything. And today we want to move on to the second part, call it what you want, MIG 102. And we want to show you the effects of some of the settings that we talked about. And so that's what we're going to do today. The camera guy will be real cool and put a link up over here, I think. And he'll reference that last video so we can kind of carry on here. I'm going to grab some fresh material, grab my notes. We're going to go through voltage plus and minus. We're going to go through inductance. We're going to go through wire feed speed plus and minus. So let's show you a couple of settings and how they play out into your weldments here. So let's get to it. Today we want to show you about 6 different conditions of things that are right and things that are wrong. The first one we showed you was the cut O-ring. We mentioned that in the previous video. And it produces, or it can produce, porosity. Remember we said we had a pair of O-rings, whatever the combination is, and most MIG manufacturers of guns and whatnot they'll have an O-ring on there, and it's to make your gas go up through the gun. Got 2 O-rings that are pretty common on a lot of machines. Keep you from going out the back end, keep you from going out the front end. We want to force it through some holes, and we showed that in the last video. But this is a cut O-ring, and it will can produce porosity. And what's porosity look like? Because we're going to show you 2 conditions here. The first one is just outright blatant porosity. The camera guy will get that. He's got some B-roll of that. The second one was kind of hidden. Well, porosity is a bunch of holes in your weld. It's like gases escaping. Some of you may be putting something together and you'll make a tack, and as it's solidifying, you'll see this thing grow up out of there and a little weep hole in it. That's porosity. So the cut O-ring can create those conditions in that we're not getting the right gas. We can show what porosity is by turning the gas off or whatever. When I get this porosity effect in the weld, the first thing I'm going to look at is the gas cylinder. Do I have gas in the cylinder? Is my flow correct? For a lot of short circuit MIG, 25 CFH is a good all-around number. And if those 2 are good, where am I going to look next? I'm going to look at that O-ring. That's the very first thing that I would check. After I check the cylinder to see if it has gas in it and the flow rate is correct, the very next place I'm going is that O-ring. The next one I believe we want to show is a voltage effect. We're going to set a baseline of like 18 volts and 200 inches a minute. And that's going to be our baseline. We'll let you see it, we'll let you listen to it. And from there we're going to deviate and go high in the voltage. We'll adjust it probably 2 volts at a time, down 2 volts at a time, and we'll go to the extreme so you can really see the effect. Next thing would be wire feed speed, just the opposite. We'll leave the voltages alone. We'll go high and low in the wire feed speed and show that effect. They are not the same. They kind of do the same thing when you're looking at them, but they are not the same thing. Want independent control, need to understand the relationship of the 2. One of them is going to be inductance. What happens with inductance when you add it, when you take it away, what happens to the weld pool. Another one is going to be your travel speed. Obviously we get an ideal travel speed. If we race forward, deviate from that, it's going to have an effect. It's going to narrow up the bead. Slow down, it's going to widen it out and stack it up real tall. I believe the last one is going to be, I believe I covered them all. No, the last one's going to be stick out. Electrical stick out, or contact tip to work distance. In short circuit MIG, a good all around number's 3/8 of half of an inch. Good condition. If we bring that back and start increasing that electrical stick out, the voltage stays the same, kind of cools the pool because the amperage is decreasing somewhat. If we cram it in there a little shorter, we don't have a whole lot of room to move between 1/2 inch down into the material from the contact tip to the nozzle, but we'll put it down there really close. We take a chance of stabbing the contact tip into the material, but it'll weld a little different, but not that much. Big one is pulling it back and sticking it out. Okay? Let's get into them. 18 volts, 200 inches a minute. because I know it welds on this particular machine. This is a ESAB Rebel 205. It's an AC/DC machine, does stick, MIG, TIG, flux core, DC, TIG, AC, TIG. Okay, so I want to run a little bit of a bead so we can see it, hear it, taste it, smell it. There's our baseline. Now granted, this material is going to try to get overwhelmingly hot, but I am going to quench it off so it's cool in between. 200 inches a minute just happened to be 90 amps on this particular machine. So from here, we want to go up in volts, and we'll go up 2 volts at a time. So we'll go to 20. We'll go to 20 volts, leave the wire feed speed the same. We get a condition that's wider, more fluid, got a heavy pop to it. And I'm going to go quench over here in the bucket just to keep this cool so you can get a true, accurate sound and sight. Excuse me, I have to go to the Coupon cooler. Okay, so we're increasing voltage and we're now up to 24, I guess it is. And we started at 18, we're up to 24. This should be a heavy, wet popping sound and look kind of gross. That would be more of the globular type transfer. It's wider. It has it had some heavy pop coming off of it. Didn't have a bunch of BBs. And so now we can go back to the 200 inches a minute and 18 volts. The 18 volts was our baseline. I don't think I need to weld again, but that's where we were for a baseline. And so from there, I'll go down 2 volts to 16, and this should sound crispy and be narrow. It's a little bit different sound, higher pitch. So this bead is peaked, narrow, and it had a crispier sound to it. I'm going to turn this down to 18, 16. I'm going to go down to 14, and I don't think the machine may not run here. I don't know. It's going to be borderline, but if it doesn't, then the machine is just going to start popping and snapping, and it's really not going to get into a weld pool deposition type. It's just going to it'll be overwhelming. And then I've got my statements after that. That is right on the cusp. It's right on the borderline of not wanting to weld it. So here's my statement. In gas metal arc welding, independent control of volts and amps, think of voltage as the liquefying effect of the weld pool. In my opinion, that's the easiest way to think of it. Amperage, wire feed speed, opposite. So we've changed just the voltage off of our baseline. I'll go back to the baseline at 18. And now would be a good time to say, let's change the wire feed speed. So we're at 200. Let's go down first, and we'll go down by 40 inches a minute each time, which is quite a bit. We better go down 30. Let's go down 30. So we're down 30 inches a minute first. Now, what do you think this is going to sound like? I think it's going to sound like a quieter weld with a little more fluidity. It's going to be a smaller weld. a little cooler weld, smaller. It was stable. Go down another 30 inches a minute. Pull the trigger. It's starting to sound like the one where we increase the voltage. There's that balance again. It's a smaller weld and it's a little cooler. So from there we'll go down another 30. Again, smaller weld, still a decent transfer as you listen to it. It's starting to sound weird, but believe it or not, that is a very useful condition for sheet metal, thin stuff. And we haven't even got to the tricks yet, and there's a bunch of them, but these are all usable conditions. I'm gonna go back to the baseline at 200. Some of these machines, as you're changing wire feed speed or changing the value, if you push in on the dial and turn it, it doesn't go by ones, it jumps by tens, and you make a big change in a hurry. So we were going down to 30 at a time, we'll go up 30 at a time. Good time to cool the plate or grab another one. I'll just cool it because the other side's good and clean. From baseline 218 volts, we're going to go up 230 in the inches per minute, up 30 from where we were. Hotter weld, tight sizzling condition, what the welder's doing fine, but we're adding more wire. So the reaction time, what you're hearing, is faster. I'll go up yet another 30. And at 18 volts, it's gonna be a while until I find that point where it just doesn't weld anymore. 230, to go 260. This one I'm going to go ahead and go up 50 inches a minute faster. I'm going to turn it up and up. But I know because it's got 18 volts behind it, it's going to take a lot of wire feed speed before I make this thing snap and pop. From here I'll get silly and go up 60 inches. No, I'll go up to 400. So we were at 310. I'll go up to 390. 80 more inches a minute. And my material's hot. I can go up a lot in wire feed speed, inches per minute. But because the plate is hot, that's helping it react, helping it weld. I'll just get silly and go to 475. It might weld, it might not. There's your borderline of, no, I don't want to weld anymore, you know. So, as long as you got a good ground and the right conditions, it'll be stable. If you don't have a good ground, you got too much wire feed speed, that's probably what you're going to listen to. You're going to hear this thing snapping and popping and bucking. So let's go back down. One of the next things we want to introduce is the effect of inductance. A lot of machine has, they have this either built in. I know some of the Miller-Matics, it's not adjustable like in the 252. Sweet running machine, very smooth. Appealing arc conditions as far as the when you set the wire feed speed and the volts. It welds super sweet. But some machines are adjustable. So we would go into a menu, and on this one I want to go up to the P's or parameters, and the first one listed is 50. I have this set at 50. All these welds that I've done before were at 50% inductance. I'll get rid of it. I push that to select it, and I'll take it down to 0. I'll select it again, it should be in circuit. I'll even take it over here where it's, okay? So all the welds done before were at 50% inductance. I've taken this out to 0. What I expect to see in here is it's hard and crispy, okay? Hard and crispy weld. To me, that was a tighter arc. It's more of a sharper sound. So if I leave the settings alone, but volts and amps I haven't changed, and I'll come back up here and I'll set parameters. I'll select inductance. From 0, I want to go to 100. I was at 50. I want to go to 100. This I expect to see smoother, wetter, widened out a little bit, a little softer sound to it, a little more fluidity. That's a welding term, by the way. Subtle, but a noticeable effect. Now, where would I set this machine for a lot of everyday use? Probably back to the 50%. If I had a situation where I was running gap on sheet metal, I might turn it down to 20% or even 10%. I'm going to take this, turn it back to the 50. I like the way it runs that way at 50. Works for a lot of different scenarios. Come on, darling, hold still while I adjust you. Boom, there we go. So inductance, you know, think of it as hard and crispy or soft and smooth. That's the best way I can define it without getting into super amounts of detail. Let's talk about travel speed. If I take off normal, we'll do one of normal speed of what I think is a decent bead. Now that's traveling along, no motion. My bead is roughly 1/4 of an inch wide, and it's the same height as I went down through it. If I increase the travel speed, my bead should get real narrow. So I started out normal. I welded normal for just a little bit, and then I took off and raced forward, not to the point where I was outside the weld pool, but my bead got narrower, a lot narrower. And then I'll slow down on this one, and it should widen out, and it should stack up quite a bit too, or some. And that is quite a bit wider and a lot taller. When I say a lot, you know, you can measure it, but it's noticeable. So that's travel speed. That's kind of a common sense thing. If you go too fast, you're not in the same place long enough. Granted, you're not going to deposit that material. It's going to be narrower. And then I believe the last one is going to be the electrical stick out, or the contact tip to work distance, CTWD. It is defined as the amount of wire that is out from the contact tip to the weld pool or to the material. It's not where the nozzle is. Contact tip is wire past the contact tip out to the weld pool. So if you have a nozzle that's recessed up inside your machine, let me clean this off quickly here. If you have a nozzle that is fixed just beyond the contact tip, meaning your contact tip is recessed up inside there an eighth, you have to take that eighth into consideration. It's not the nozzle, it's from the contact tip. So this one is flush, and this amount that I have sticking out here is correct for most short circuit gas metal arc welding conditions. The condition would be stable. It's going to allow you to maintain your nozzle. You're not going to get a bunch of dingleberries and huevos and whatever you want to call them. It's just the right thing to do. If you increase the stick out, what are you changing? Well, it's a constant voltage machine, so the voltage should stay the same. You're decreasing the amperage. And it gets weird because you get out here so far, you're not in your shielding gas anymore. You get porosity. You also get out here long enough and the machine will just start going nuts. It won't weld. So let's weld normal first. We like that sound. And now I'm going to decrease the stick out. I'm going to almost stick this contact tip down in the weld pool, which I feel very nervous about because I don't think I have a backup yet. So let's do that. I'll get down closer. So that's normal. And that's down there getting close. It doesn't have that big of an effect when you get from ½ inch down a little closer. The big effect is when you start pulling it back and increasing it. I mean, that's beyond excessive right there. But that's a testament to these machines. I did a video on another color of machine, and I mean, it's amazing how these little inverters, they just want to keep welding when you destroy conditions. So for a hobbyist or a beginner getting into this, you get into one of these new machines, these new inverters, you've already got a lot of stuff working for you. They try to weld and correct a lot of things. I think it was about right in here, good 1.5 inches. I mean, look at our weld pool. It gets peaked, it's rounded up, and at the very end of this, I see a little bug hole. It's got to have porosity in it. It has to. I'd even bet the camera guy $10. If there's porosity in here, collect $10 off the camera guy. I'm saying it's there. He didn't want to bet, but there it is. So it was kind of hidden in there, but I could see it as the weld pool was going in. And it's hard to listen to, but you know. So that's what you get with increased electrical stick out. And that's for hard wire or solid wire gas metal arc welding MIG short circuit. 75-25 gas, We established the baseline at 18 volts and 200 because that's kind of the best way to show it. There's all kinds of settings, and they do have an effect on different types of welds and weld joints. If you're just getting into gas metal arc welding, you want to learn this process, if you need help, definitely holler at us. We'll walk you through it. I've taken a piece of plate. Here would be an assignment. We try to run straight beads, straight lines, same height, same width. And so I've scratched some of these in with a file. You can do it with a scribe. I've put some of them in with soapstone. Weld between them, weld over the top of the line. But as you're putting beads down, try to blend them together. By blending, I mean, I don't have my soapstone on me. By blending, I mean, make them melt together. You point the wire into the previous weld, the edge of the previous weld, which is called the toe. And it's the fastest, easiest way to learn how to blend beads together. So let me start this out for you. The edge of the plate is straight. That's a good guideline. Here's what I mean by pointing the wire into the toe of the previous weld. Toe of the previous weld is right there. When I put these other beads on there, it should blend about halfway into the other bead. Watch your eyes. And we would do that for a series of welds. We cool the weld pool or cool the plate off and just keep going. If you're doing this, you're teaching yourself how to run straight welds. And when you're doing a repair or a fabrication or something, a lot of times you're not going to be able to make a great giant weld in one pass, and you don't want to. Let me run another one of these. That one I could see better. I positioned my head around here. So you can see that we'll get this built up a little bit, but they're all the same height and same width. And that's what you want to practice. Practice that in stick welding, practice it in MIG welding, TIG welding. When you master all that, yeah, it seems simple, but you have taught yourself a lot. You've mastered a lot already. The simple stuff matters later on. So we went through MIG 101 where we put the gun together. We've done settings on part 2 or MIG 102. We're going to start getting into various joint configurations, lap, T. We'll get into the groove welds. We'll get into positions. There's a lot of variables. There's a lot of things to look for, none of which are hard. They're not really hard. Just pay attention to some of the things that matter, the position, how much weld do you want to carry? What's the joint configuration? What are the requirements? What's the material? Okay? So I have some other information. It's not welding, it's written, it's verbal, but it matters. It's easy to explain. I think we'll put that in the next video as a reference to the next video because it blends in nicely. It's a good intro into groove welding and structural welding, lap welding and stuff. I hope this helps. Let us know in your comments where we need to go in the direction. We'll do it with, there's so many things we can do this with. MIG welding, structural carbon steel, stainless steel, flux core. There's a couple different types of flux core wires. There's a lot of stuff to learn and a lot of applications. So that's it for part 2. I'm Bob Moffitt. Let's Weld Something. We're in Chicago, Illinois. Camera guy's having fun. He wants to go eat dinner. So let's close this out. Thanks for watching. Please subscribe. Hit that bell button there to get the notification of when good content comes out. Thank you very much.